All right, chumps, let's do this.
We're getting to the formulation.
All right, today class we're going to learn about hypercubes and how to visualize them in your brain.
Yes. No, so we're going to take flat Earth theory apparently.
So all the other planets are spheres, but Earth is flat.
Earth is flat. I mean, I can just see it for myself.
Yeah.
Have you heard about that, the Elon Musk tweet to the Flat Earth Society?
No.
Okay.
It's basically that. He says if there's a Flat Earth Society, why is there no Flat Mars Society? And he tweeted back that unlike Earth, we can observe Mars to be round.
Flat Earth Society was like, we can see that Mars is
We
round.
see that Mars is round, and I'm like, yeah.
The person with that Twitter is the person
I
that
don't
owns that Twitter is
understand.
probably like some 13-year-old in their basement.
Whoever has the Flat Earth Society Twitter handle.
Some fucking 13-year-old in a basement, just fucking with everyone.
And then they're like, checkmate.
QED.
Yeah, it's like what they said. They expect to be like, oh yeah, I never thought of that before. Right, you know.
That does make sense.
Yeah, that does make sense, right?
Cool.
So let's review a little bit, not go through all this derivation again. But RIX was the number of reactions per cubic meter per second, talking about nuclear reaction rates. And that was the number density of species I and times the number density of species X, the two species that are interacting with one another, times this integral over velocity, or over energy, I meant to say, of cross-section in the center of mass frame as a function of energy, center of mass frame relative velocity, P of VDE, where P of VDE is the probability of the particles having that relative energy in the center of mass frame coming from the Maxwell-Boltzmann distribution. And then I had mentioned that joyful homework is to show, using the Maxwell-Boltzmann distribution, that you can rewrite P of VdV, the probability that the particle's speed is in between v plus dv. You can turn it into an energy probability. P of VdE is equal to 2 over square root of pi, pi to the 1/2, times kt to the 3/2, times the square root of the energy, e to the 1/2, times exponential, e to the minus e over the thermal energy kt, e.
It took me a while because I did homework a while ago, so I didn't remember.
And yeah. Right. Well, that's what you. The joy's coming back now.
Yes, it is.
Yes. Have you had that joy yet?
No.
Oh, okay. Well, you've got something to look forward to.
Yes.
Right? So now, it is useful to factor out the predominant energy dependencies of the cross-section, sigma v. So we're going to write that sigma v, by definition, is capital S of v, and we'll say what that is in a minute, times the effective cross-sectional area. Cross-section has the same units as area does, so it makes sense that there is some sort of cross-sectional area here, and we'll say what we mean more precisely in a minute, times nuclear reactions, and so we want a term which represents the probability of barrier penetration, how likely it is to actually get in there and fuse. So S of E is the hand-waving term. It is a, we hope, slowly varying function of energy that accounts for the gory details of the nuclear physics. I think that, the word gory never comes separate from details in my experience. It's always gory details. I guess you could say it's a gory something rather than being kind of scary.
Whenever I think of the word gory or gore, my mind immediately goes to video games.
Oh, yeah?
Mm.
Yeah.
I don't think I've ever heard right that much.
Gory,
I can say it, but
Yeah.
The
There's a first time for everything.
first really bad video game that I had was right down for in school. It was more of a fun. Great game to give you like. My question is why the chicken feet upside
Because I'm waving,
down? Oh,
and they're supposed to look like hands.
I know.
So that's why they're upside down.
That poor chicken.
I know, it's like,
It's not even doing that. They're holding the hands like this. It's probably dead.
well, that's true. Unlike the cute little bat that the student observed is hibernating in there and doesn't care when you rotate the dome or open the dome. So the cute little bat just like, whatever.
You should name it.
so it's not the cute little
Shit.
bat that's in the curtains.
No, it's not. It's that cute giant bat. Oh, did they tell you about the cute giant
I
bat?
think we've all heard the story of the giant bat.
Which is still better than the one I found dead under the chair one morning.
Oh, that's over.
Oh, that was great, yeah. And I moved the chair to put it back in place, and there's a bat, just dead.
I feel like that's a bad moment in Harry Potter or something.
So anyway, the effective cross-sectional area is pi lambda squared, where lambda is the wavelength. So, in other words, we kind of think of the area of a circle of radius lambda is kind of how it's written, so to speak, equals pi h over p squared, the Broglie wavelength. Because remember, we're saying stuff about you need to get within about the Broglie wavelength for a significant probability of tunnel. Was our idea, and that in itself was chicken feet, right? We're just saying it turns out that. So that's pi h squared over 2 times the reduced mass times the energy, because remember that E is p squared over 2 times the reduced mass, right? In other words, that's another way of writing kinetic energy. And so p squared is 2 ue, in other words. So it goes like 1 over the energy, and then we might as well just take this part and fold it into S of E. Why keep it separate? So we just multiply S of E by that, it's a constant, and we just call that S of E. So there's no reason to keep the other piece, so just leave it as the 1 over E, essentially.
What does fold it into?
In other words, whatever your S of E was, multiply it by that. Take the pi h squared over 2 mu and just multiply that by S of E and then call that S of E.
Okay.
So that this just becomes S of E times 1 over E for these first two terms. Comes from cooking, where you fold eggs into the batter, and just take the eggs, you just mix them into the batter, and now it's the batter.
Your mathematical batter.
Your mathematical batter, that's right. Yes. A little pi here, a little h squared there.
I smell the rotten
Pretty soon you've got a delicious cake. So no, you've got a delicious pie, 3.14.
Got the butter on the moon.
Uh-huh. A great cook never measures. A mathematician doesn't either, but a physicist does. A detailed quantum mechanical treatment shows, in other words,
That hurt me.
more chicken feet.
That sentence hurt me.
So in other words, it's helpful to take this and make it 2 chicken feet times 1 over times 1 over feet. Or 4 chicken feet, because we weighed 2. Shows that the probability of barrier penetration goes like this. Probability. The tunneling probability, would be another way to put it, goes like e to the power of minus 2 pi squared times UC over E, where UC is the height of the Coulomb barrier for a radius equal to the de Broglie waveform. That's too low. And that gives you time to catch up. I'm going to leave that up there because we're going to refer to it again. UC equals height of Coulomb barrier for R equals lambda equals H over P H over reduced mass times V. So what we mean by that is, remember that the potential looks something like this. And so what we're saying is, let's say that's R equals lambda. Then that's UC, the height of the Coulomb barrier for R equals lambda, which is related to the energy. So implicitly, this is all related to the energy. So UC is equal to Z1 Z2 E squared times mu mv divided by 4 pi epsilon naught h. Because remember that the Coulomb barrier is Z1 Z2 E squared over 4 pi epsilon naught R, right? The Coulomb potential is Q1 Q2 over 4 pi epsilon naught R. So that's just Q1, which is Z1E, charge on the first nucleus, times Q2, Z2E, charge on the second nucleus, over 4 pi epsilon naught times R. And 1 over R is mu v over h, because R is h over mu v. So that's just as advertised, the Coulomb barrier at R equals lambda. So let's note that UC increases as V increases. Which in and of itself is working against us. The taller the Coulomb barrier, the harder it is to get through it. So if the particle is moving faster, what happens to its de Broglie wavelength? Well, if the particle is moving faster, what happens to its momentum? Faster particle has A, bigger, B, smaller momentum. Bigger momentum, and the de Broglie wavelength, h over p, means that its wavelength has become smaller, right? So the faster the particle is moving, the smaller lambda is, the bigger is the value of uc, is the idea there.
What is the value of UC 160?
Yes, that's right. Some further decoration so that you remember the argument later.
We've got to go hard, it's the end of the class.
Yeah, that's right. So UC over E, which is showing up in the barrier penetration probability there, is e to the minus 2 pi squared UC over E. UC over E will be UC over the kinetic energy minus 1/2 reduced mass V squared. So that'll turn this into 2 times Z1, Z2, E squared over 4 pi epsilon naught HV. In other words, just take this prior expression and multiply, well, divide by 1/2 mu V squared. And so the mu's cancel, and then you got a 1/2 that comes up in the numerator as a 2, because I left that as a 4, because 4 pi epsilon not so important that you just leave it together. And then you got v over v squared, which is 1 over v. So note that what we're having here is that E increases as v squared, or in other words, faster than UC does. So this ratio, so UC over E decreases as V increases. So even though the Coulomb barrier is getting bigger, the energy gets bigger. As V increases, the energy gets bigger faster than the Coulomb barrier gets taller. And so what wins is the increase in the energy, so to speak. Well, let's put in that V is 2E over mu. So this becomes Z1, Z2 times E squared, and now I'm going to break my ruler on the next line. 2 over 4 is a 2 on the bottom. I could keep it separate, but something possessed me in the notes not to, and I don't want to screw myself up by deviating and forgetting something. 2 pi epsilon naught h, and then 2e over the reduced mass to the 1/2. V is the square root of 2e over mu. So I put in V is the square root of 2e over mu. And then if I'm actually writing this in my notes, I write this on the next line, but I don't want to write it on the wood. Pull up the other board, so I'm doing it this way. So if you simplify all that, that is reduced mass to the 1/2 power Z1, Z2, E squared over 2 to the 3/2 power, also known as the square root of 8, pi epsilon naught h, and then finally times e to the 1/2, capital E to the energy to the 1/2, minus 1/2, right? Yeah, minus 1/2, because it's down in the denominator. So that barrier penetration capability is proportional, as we said, by waving our hands, e to the minus 2 pi squared UC over E, but we just got an expression for UC over E. We'll say this is equal to E to the minus B, E to the minus 1/2, because UC over E was a bunch of junk, times E to the minus 1/2 power. So the B will be the 2 pi squared times a bunch of junk. So B is this mess. Pi times reduced mass to the 1/2 Z1, Z2 E squared divided by 2 to the 1/2 epsilon naught h. So that B there was just all that crap over there multiplying e to the minus 1/2 times 2 pi squared. So pi squared over pi becomes a pi, and 2 over 2 to the 3/2 is 1 over 2 to the 1/2. Let's note that B depends on the electric charges of the fusing nuclei. It's got the Z1 and Z2 in there. And furthermore, as you would expect, increasing the charges decreases the reaction cross-section, because this is e to the minus b, e to the minus 1/2. So the bigger Z1, Z2 is, the bigger B is, the smaller e to the minus b all that crap is. So in other words, it's harder to fuse if the charges are bigger, and that makes sense. The bigger the electrical repulsion, the harder it is to get them to fuse. increasing the charges decreases the reaction cross-section as we would expect. Due to the greater Coulomb repulsion. So if we collect everything, thus finally, sigma v, we said was going to be factored into S of E, and then times those other terms, well, those became e to the minus b e to the minus 1/2 for the barrier penetration probability term. And the term in the middle, the effective cross-sectional area, looked like 1 over E. Okay, any questions? All this glorious curiosity. So, let's put all that into this integral here.
Well, I guess I really, what does it mean by greater repulsion?
In other words, the more protons that are in the nuclei, the bigger is the Coulomb repulsion between them, the force between them. So it's harder to fuse 2 heliums together than it is to fuse 2 protons together, because if you fuse helium, you've got pairs of protons in each nucleus exerting repulsion, as opposed to single protons. So the higher the charge on the nuclei, in general, the harder it is to fuse them. Now, there are exceptions to that rule because of the details of the nuclear physics, the strong force interaction and all that. But in general terms, heavier nuclei are harder to fuse because there's more protons in them, and so they repel one another more. So, Rix is this integral right here. And Inx, integral from 0 to infinity. And now let's put in what all the terms are. The sigma of E is that stuff over there. S of E times E to the minus B E to the minus 1/2 divided by E. So that piece is sigma of E times V of E is the square root of 2E over mu. Right, that's just the speed is the square root of 2E over the mu over the reduced mass, since E is 1/2 mu V squared. And the P of E is from the joyful homework, the 2 over pi to the 1/2. I only assign joyful homework, as you notice. Never, ever have you thought, oh man, this problem is really frustrating.
It's never frustrating.
No, you just thought, wow, I'm enjoying this challenge, and that is bringing me joy. And if I say that often enough, maybe you'll believe it.
As I say to the registrar.
Right.
I'm really enjoying this problem.
There's the P of E. Or putting everything together, Rix is 2 over kt to the 3/2 power times ninx over reduced mass times pi to the 1/2 power times the integral from 0 to infinity and beyond. S of e to the minus b, e to the minus 1/2. These are e's, of course. One's the energy, one's the base of the natural logarithms. E to the minus e over kt. dE. Because notice here, this e gets canceled by that e to the 1/2, and that e to the 1/2, so that e drops out. So this is the one that gets the box. That's the integral that you actually do in order to calculate the reaction rate. Of course, you'd have to know what S of E was in order to do it. Tis a doozy, yes. So let's take a break. Even though we started a little late, and we were guessing a while, so we're almost done. So we'll take a little break.